Some of the most difficult concepts I've had to teach in calculus involved what I called particle motion. There are really 3 programs in this one program, and I haven't looked at it in a couple of years, and I see that it's kind of confusing. So if you've never seen it before, of course it's going to be confusing to you. There are 3 things in particle motion and velocity all packaged together. They were all taught at the same time in the book I was using. So we study particle motion using the position graph, and study particle motion with the velocity graph, and then study vertical motion. Let's look at the vertical motion one first, because it's the most straightforward. I don't even think I'll work a whole problem. This is really where calculus and physics meet. And I have this little rocket that's shooting up in the air. And if we graphed it on time against time we're shooting, it's just going up and down. But if you made the x-axis be time, the graph would look like a parabola. And we studied these in the lower grades sometimes, and these problems are kind of limited because you've got to have a certain units of gravity, and they're sort of all the same. So I'm going to ask a question here and generate questions. And sometimes I change the units, like this one's meters, some of them will be in miles per hour, and here it gives you the formula for acceleration due to gravity, but this one's in meters per second. And a projectile shot upward with this, and you are asked to calculate the first and second derivative because they all have meaning in physics. This is the position of the object when you shoot it up. Its position can be solved by putting the time in, and then if you wanted to know how fast it was going, then you would use the first derivative, and if you wanted to know the acceleration, you would use the second derivative. So when you do one of these problems, you're going to need all of those, so you just take the derivatives, and then eventually it's going to ask you what's the maximum height, how long is it going to take, and it's just going to generate problems for you of that type. Let's go back to the main menu and look at the more sophisticated. I put this in at the end. I found that those students who had taken physics had no trouble with this projectile motion, and they're pretty straightforward. We do study them in the lower grades as well, even before we know how to take our own derivative. They just give the kids the velocity formula, and in the lower grades they postulate it. Let's go back to the main menu. The reason I wrote this is these 2 things, because the AP people make a big distinction between giving you a graph of particle motion, position graph, and particle motion, the velocity graph. So let's look at the position graph here. And I have, instead of making 5 or 6 different programs, I just give you a graph, and you can make any kind of graph you want. It's going to generate them. And then you can concentrate on the various kinds of problems that you have. This is one kind of problem. This is another kind of problem. This is another kind of problem. This is another kind of problem. And I usually had the students use these and work on the sections that they had trouble with. So right now we've got this particle, and this is the position graph. So what it's showing is where is the particle. And this goes from time 0 to time 10 seconds. When time starts here at time 0, this particle is to the left of the origin, or the -1 from the center. And then it moves to the right, and then it moves further right, and then it moves back. And I thought I'd make an animation that related to this. So we're going to show the motion of the point, and you can see I'm following the graph here, and you can see where it's at. It's there, and it's moving left, and then it's moving left some more, and it's moving left some more down to the origin, and then it's going to move back up, and then it moves back down and down. So this red point is following, if I show the motion, starting here at -1, and then it's at 0, and then it's at 1, and then it's here, and then it's there, and then it's there, and there. And so you can see that below the x-axis it's negative and above it's positive. So we want to be able to answer what direction is the particle moving. So I'm going to click on this. Is it moving right or is it moving left? Well, it's going down, so it's moving left. Left. New location, moving left. Correct. This is the position vector. It's moving right. I should probably create a new graph because there would be some, we'd probably, if the AP people ask you, they would probably put some place where the thing was standing still, which would be right here. On the position graph, if it's not moving left or right, it's standing still. So, new location, it's standing still. New location, moving left. To find the average rate of change over the interval from 0 to 10, you would figure out where he was when he started, where he is at the end, and it's the average rate of change is the different final position minus the initial position divided by the 10. So if we did that, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. It's they're moving 9 over the 10 times, so it'll be 0.9. Check, we win. And there it's showing you the rate of change is 9 divided by the 10, the average rate of change, the slope of this line. And we can change this graph anytime we want. And now we want to graph the derivative of this. So right here we want to graph the derivative right in this little interval here. Oh, the derivative of this would be the slope of this line. So this one would, in order to check this, you move this up. The slope here is 0. Check, we win. New location. What's the slope right here? 1, 2, 3, 4, 5, 6 divided by 2. That would be -3, so we'd come up here. The derivative would be the velocity. It's -3. Check, we win. Now, if we graph the speed in this same region, speed is not the same as velocity. Speed is the absolute value of velocity, and we were lucky here that it came out to be the same one. The velocity here was -3, but the speed is, I used to joke with the kids and say, if you go to school and you decide you're late and you don't want to speed, it doesn't count if you drive backwards 50 or 60 miles an hour on a 30-mile-an-hour thing. Speed is the absolute value of the velocity. And I put some things in here if you sort of want to check, you can graph the velocity locations all at once and see what they are. They're positive and negative. The speeds are positive, or take all the negatives and make them positive. So this is the position graph. Get it fixed in your mind. This position graph shows you where the particle is located in the position in 10 seconds. Now, if we go back and we come to the velocity graph, we're not looking at where the particle is. We're looking at its velocity. So this changes everything, and it is a great favorite of the AP people to give you a graph and then ask you, where is this standing still, for instance? And I'm sure they lure a million kids into saying it's right here. But actually, what's happening here is this is the velocity. Here, the critter or particle is going whatever unit of measure, say that we're going miles per hour. These going -3 miles per hour, then -2 miles per hour, then 0 miles per hour, then -1, then -2, then 0, then 2, 2, 2. I tell the kids on the velocity graph, the level lines are not him standing still. That's when he's got the car in cruise control. So here he's speeding up, speeding up, slowing down, speeding up, cruise control, slowing down, slowing down. So the kinds of questions that they're going to ask us, click a place where is the speed of the particle is at its maximum. So this is the velocity graph. Now remember, speed is the absolute value of velocity. So where does the velocity make its maximum value? That would be here. And we could graph the speed automatically. You can see the speed is the absolute value of the velocity. These are negative, and these would be, the speed would be the green line there. So we could graph it says graph the derivative of this. So this one would be 2, the slope of this is 2. So we check and we win. So they're going to ask you when they're speeding up and when they're slowing down. Questions about the graph. Oh, here we go. At what location is the particle moving? I guess I'm asking about the here. Is it moving right or is it moving left? It's positive, so it's moving right. What's it do? Which direction is the particle moving? The velocity is negative, so it's moving left. It's negative, so it's moving left. It's positive, so it's moving right. It's negative, so it's moving left. It's a little hard to get, but you got to think that this is a picture of velocity. Then we can do the average rate of change find the average rate of change, units per second, of the average change in the velocity. So we can do that, making that triangle like we did the last time. I think I better quit because my dog is getting impatient with me. I hope you can figure this out. I think it should help you with some of the AP questions, but you really have to work at it. I had my students do several 10 or 15 minute sessions on this till and the ones that worked on it got them right on tests. So thanks. Bye.